In section 10.4, we look at solving nonlinear systems of equations. So a nonlinear system of equations is when you have two functions and at least one of them is not a line. And what you're doing is you're trying to find the points of intersection of the two curves. So I have some graphs here just to kind of give you an idea of the types of situations that we'll be dealing with. So for example, you could have a circle and a line. This is a nonlinear system because the circle is nonlinear. It's not a straight line. And in this case, you can see that the line intersects the circle in 2 points. And so you would have two solutions for this system. But you could have a circle and a line where the line is tangent to the circle. And in this case, there would only be 1 point of intersection, so only one solution. Or you could have a circle and a line that don't intersect at all. And in that case, you would have no solution. So what you should see here is that depending on the situation, you could have any number of solutions. Down below, I have a slightly more complicated scenario. Here we have a circle and a parabola, and in this case, the parabola intersects the circle in 3 points, so there are 3 solutions. And in the final graph, we have a circle and an ellipse. And in this case, they actually intersect in 4 points, and so there would be 4 solutions. Now, to find our solutions, we are not going to be using graphical methods. We are not going to graph to find solutions because graphing does not give precise answers. So I give you some hypothetical graphs here on this page just to kind of motivate the discussion that we're about to have. But to find solutions, we have to do this purely algebraically. So we're going to solve a few of these systems of nonlinear equations, and I will sketch the graph at the end just to verify our solutions, but I want you to understand that we will not be graphing as a primary method for solving. Let's take a look at some examples. So in our first example here, we have an equation 2x plus y equals 1. This is a line. And x squared plus y equals 4. This is a parabola. Now, when you're solving systems of nonlinear equations, you can use either substitution or you can use elimination. Most of the time, you will probably be using substitution, as it seems to be the method that works a little more often. So when you use substitution, remember the fundamental principles. So first of all, what I'm going to do is take one of the two equations and solve it for one of the variables. So let me just take the first equation here. We have 2x plus y is equal to 1. And if I subtract 2x from both sides, we get y equals 1 minus 2x. The second equation is x squared plus y is equal to 4. And so just like we did earlier in the course, we're going to take y equals 1 minus 2x and substitute the expression in for y in the other equation. When we do that, we get x squared plus 1 minus 2x, so that's being substituted for y, is equal to 4. Now, there's actually no need to have parentheses here. I put parentheses to indicate that this was being substituted in for y. But you should notice that this is just a quadratic equation. So we have x squared plus 1 minus 2x is the same as minus 2x plus 1 equals 4. And now we'll solve this by subtracting 4 from both sides. And that gives us x squared minus 2x minus 3 equals 0. Now let's go ahead and bring that equation up here. And you can use any method you like. So if you like the quadratic formula, you can go ahead and use that method. I'm going to go ahead and factor it. Factoring is relatively simple here. And then, of course, we set each factor equal to 0. And we get two solutions. We get x equals 3 or x equals negative 1. Now, these are not the points of intersection. These are the x-coordinates of the points of intersection. So what I'm saying is, for each one of these, we have to find the corresponding y value that goes with that x value. And so to do that, I'm just going to go back to our original equations. In fact, I think I'll go to the one where I substituted because that's the easiest one. So I'm going to bring this over here. We know that y equals 1 minus 2x. And I'm just going to take each of these x values and plug it into this equation to find the corresponding y value. So when x equals 3, y will be 1 minus 2 times 3, which is 1 minus 6, and that gives us a y value of negative 5. And when x equals negative 1, y will be 1 minus 2 times negative 1, which is 1 plus 2, and that's the same as y equals 3. And so our 2 points of intersection here are the points 3, negative 5, or negative 1, 3. And so this system of equations has two solutions. No graph is required. However, I am going to bring in the graph so that you can actually see these solutions. So let's import the graph, and I want you to visually check to make sure that these actually are solutions. All right, so here's the graph. We have the first equation, 2x plus y equals 1. That's a line. And the second equation, x squared plus y equals 4, is this parabola. And you can see that there is 1 point of intersection right here, and there's 1 point of intersection down here. The first point of intersection has coordinates, let's see, that's negative 1, and that's 3. So this point would be negative 1, 3, and that is consistent with what we have down here. And the second point has an x-coordinate of 3 and a y-coordinate of negative 5, and so that is the point 3, negative 5, which is this one down here. Okay? So we can graphically verify our solutions. But could you imagine graphing these things in order to find the solutions? That would be a harder process. Generally, most students find graphing to be a more difficult process. So again, I'm only using the graph to verify the result. Let's take a look at a few more. All right, so for our second example, the first equation here, x squared plus y squared equals 13. That is a circle of radius square root of 13. And the second equation, y equals x squared minus 1, is a parabola. All right, so I'm going to go ahead and use substitution once again. And this one's actually kind of nice because y equals x squared minus 1 is already solved for y. So we can take that expression and we can substitute it in for y in the first equation. And so if we do that, the first equation becomes x squared plus x squared minus 1 quantity squared is equal to 13. So now we have to multiply this out. So remember, when you square, it just means you're multiplying by itself. And x squared times x squared is x to the 4th. And then negative 1 times x squared is negative x squared. And negative 1 times x squared again is negative x squared. And then plus 1 equals 13. combining like terms, we have x to the fourth minus x squared plus 1 equals 13. And so what I did there is I just said that this x squared and this negative x squared cancel. And then finally I can subtract 13 from both sides. And when I do that, I get x to the fourth minus x squared minus 12 equals 0. Okay, so this is a fourth degree equation, but we can solve it by factoring. So when we factor, we'll have x squared and x squared. 12 will be 3 times 4. And we'll have a negative 4 and a positive 3. And then from there, you can set each factor equal to 0. So we can set x squared plus 3 equal to 0, x squared minus 4 equal to 0. And by subtracting 3 in the first equation and taking a square root, you can see that x will equal plus or minus I times radical 3. So those are two solutions for x. And if we solve the second equation by adding 4 to both sides and then taking the square root, we end up getting x equals plus or minus 2. So we have 4 solutions for x. However, if you're trying to find points of intersections of graphs, imaginary numbers do not show up in those graphs. So because we're talking about graphical solutions here, we're going to discard these two answers. They just cannot be. So that means we actually only have two answers. We have x equals 2, or we have x equals negative 2. And we can find the corresponding y value by simply plugging those back into the original equation. And so y is equal to x squared minus 1. And so this is 3. And for the other one, y equals x squared minus 1. And this is also 3. So one solution is x equals 2, y equals 3. The other solution is x equals negative 2, y equals 3. Okay, so these are the solutions to the system. Now, once again, I'm going to go ahead and bring in the graph just to verify, just to show you that it actually makes sense. So let's bring in that graph. Okay, so here are those graphs. Y equals x squared minus 1 is this parabola here. And x squared plus y squared equals 13 is this circle here. And we can see very clearly we have a point of intersection here, which occurs at the point 2, 3. And we have another point of intersection over here, which occurs at the point negative 2, 3. And those are consistent with what we found algebraically. All right, so for our next example, we have actually a hyperbola here, and we have an ellipse here. And graphing this would be really difficult, I think. But again, we can solve this algebraically by either using substitution or by using elimination. And for this problem, I'm going to use elimination just to show you that you can use an alternative technique. And one of the reasons I'm choosing elimination is because notice that we have like terms here, these are x squareds, and like terms here, y squareds, and like terms on the other side of the equation, since those are just numbers. So what I'm going to do is take that first equation and I'm going to multiply both sides by 2. Now, why am I doing this? The reason why is because when you do 2 times negative y squared, that will give us negative 2y squared, and that will cancel with this positive 2y squared. So that first equation, when you multiply by 2, is 2x squared minus 2y squared equals negative 10. And the second equation is the same. It's 3x squared plus 2y squared equals 30. And now I can simply add these two equations together. And what happens, of course, is these cancel out. We have 5x squared and negative 10 plus 30 is 20. And then we can divide both sides by 5. That gives us x squared is equal to 4. And by taking the square root of both sides, we get x equals positive or negative 2. Okay? Now from there, we have to find the corresponding y values. So we're going to take x equals positive 2 and x equals negative 2 and plug those into one of the original equations and solve for the other variable. I'm going to plug it into the first equation, but I'm going to do something to that first equation first. So the first equation is x squared minus y squared equals negative 5, and I'm going to be solving for y. So what I'm going to do here is add 5 to both sides and add y squared to both sides. And when we do that, that's going to clean up the equation a little bit. We're going to have x squared plus 5 is equal to y squared. Okay, so that's what I'm going to use to find my y values up here. So let me go ahead and write that down. Y squared is equal to x squared plus 5. And so when x equals 2, y squared will be 2 squared plus 5. This tells us that y squared will equal 9, and by taking the square root of both sides, we actually get y equals positive or negative 3. So we get 2 answers for y. Let's think about what that means. When x equals 2, y can either be positive 3 or negative 3. So that means if x equals 2, y can be 3, or if x equals 2, y can be negative 3. So we end up getting 2 points of intersection just from that one. Then we do the same thing with x equals negative 2. So we're going to plug that in to our equation. Y squared will be negative 2 squared plus 5. Well, this is also 9. And if we take the square root of both sides, we end up getting y equals plus or minus 3. And so once again, we get 2 values of y for this single value of x. So that is going to give us 2 more solutions. So x equals negative 2, y equals positive 3, or x equals negative 2, y equals negative 3. And we end up with 4 solutions. Now, to make us believers, I'm going to go ahead and graph each one of these. Again, remember I told you this was a hyperbola and this was an ellipse. And so let's take a look at that graph. All right, so there it is. So again, the hyperbola here is x squared minus y squared is equal to negative 5. And the ellipse down here is 3x squared plus 2y squared is equal to 30. And you can see that we have points of intersection. We have one point here, that is the point negative 2, positive 3. We have a point here, which is positive 2, positive 3. We have a point down here, which is 2, negative 3. And finally a point here, which is negative 2, negative 3. And you'll notice that those are the same answers that we got algebraically. So it's pretty cool because this stuff works. It's sort of the culmination of everything that we've done in this course. It all kind of comes together in this section here. Let's do one more example. All right, so for our last example, there's actually nothing spectacular about this problem. We have a line, 3x plus 2y equals 10, and we have a parabola, y equals x squared minus 5. And I'm going to go ahead and use substitution. I can take this expression and substitute it in for y there. And when we do that, we get 3x plus 2 times the quantity x squared minus 5 is equal to 10. Simplify, this is 3x plus 2x squared minus 10 equals 10. And I'm going to subtract 10 from both sides to get 0 on the right side. And on the left side, I'm going to put it in order. So 2x squared plus 3x minus 20 equals 0. Now, I'm going to factor this, and again, you can factor this if you like, or you can use the quadratic formula. It's really up to you at this point. Factoring for me is relatively quick and easy, so I'm going to say 2x squared comes from 2x times x, and 20 in this case will be 4 times 5, and the reason I'm picking 4 and 5 is because 2 times 4 is 8, 5 times 1 is 5, and 8 take away 5 is 3. So we need a negative 5 and a positive 4. And then, of course, we set each one of these factors equal to 0. And this gives us two values for x. We're going to have x equals positive 5 halves, or x equals negative 4. And then, just like before, we'll take those values and we'll plug them into this equation here to find our corresponding y value. And so when x is 5 halves, well, that's kind of ugly, isn't it? It's 25 fourths minus 5 is the same as 20 fourths. And so if we do the math there, we get 5 over 4. So the point of intersection there is 5 halves, 5 fourths. And when x equals negative 4, y should be negative 4 squared minus 5, which is 16 minus 5, which is 11. And so that gives us the point negative 4, positive 11. And here are our 2 points of intersection. And one thing that's a little bit different about this problem is you'll notice that the first point has fraction values. And if you were trying to solve this by graphing alone, it would be really hard to try to determine what the coordinates are of that particular point by graphing. But you can see algebraically, there's no issue with finding that point. So let me go ahead and bring in the graph here. All right, so here's our graph. Okay, and let's verify those points of intersection. So we have a point of intersection here, which corresponds to x equals negative 4 and y equals 11. So that would be the point negative 4, 11. That's this one. And then we have a point of intersection here. And you'll notice that this is kind of difficult to see what the point is. The numbers here are 1, 2, 3, 4. So the x value is between 2 and 3. It's actually 2.5, which is 5 over 2, and the y coordinate is right there, just a little bit higher than y equals 1. It's actually 1 and 1/4, which is the same as 5 fourths, and so that is this point here. So again, if you were just trying to find that point of intersection using the graph, that would be very difficult to do. See, this is why graphing is not a very good method for finding precise answers to these systems. Okay, so we want to make sure we use algebra to find these solutions. All right, time to get some practice.